particular problem. So you can already see that I'm starting off with an expression that we had derived a couple of recitations back. So that's an expression for finding out the damping ratio for a specified overshoot value. And we need that for this particular problem, and I'll show you how just in a moment. But just to jog your memories, I already have that expression written down over there. So in this problem, we have been given that the overshoot value is 10%. So as you can see, we can very clearly plug that into this expression that we had derived earlier. And we also have a damping ratio for our system. So now what they're asking us in a sense is that find out the value of gain for which our damping ratio or our overshoot percent matches this specified value. So it's a bit of a tricky task to do if you were to do this with hand. So we will need a little bit of help from MATLAB as well. And I'll show you how to do that. So first of all, let's just start off making our imaginary plane. So I have my real axis, I have my imaginary axis, and on the imaginary plane, as you guys remember, there are a couple of ways of describing, like constant lines of natural frequency, constant lines of damping ratios, right? So here we will need the constant lines that represent a specific damping ratio, and those can be defined by the straight lines that have a slope which make an angle theta. And if you're looking at any point on this line, it would be something like this. So the magnitude of wherever it is would define the natural frequency. The imaginary axis component is omega d, and that's also a term that we had defined when we were deriving that expression a couple of recitations back, so you can go back and take a look at that. We won't need it today, although. And then the real axis part would be that. So clearly you can see that if you were defining, if you wanted to define this damping ratio line, we just need that angle theta. And cosine of theta is nothing but that. The damping ratio times your natural frequency divided by your natural frequency. Just looking at this plot here, you can see that these natural frequencies kind of cancel out, and you can see that, yeah, this line is only a function of the damping ratio. So you can find out theta by cos inverse of whatever your damping ratio is. So from overshoot, we turn that into the damping ratio. From the damping ratio, we turn that into theta, which gives us a graphical line on our imaginary plane that we can use, or rather, we know that this is what has to intersect with our root locus to give us our solution. Right? So now we have this line, we have defined it. Let's go ahead and calculate some numbers. So for our particular problem right now, the damping ratio turns out to be around 0.5912. And if you were to plug that in to find theta, you have theta as approximately 53.76 degrees. Right? So we know this line, and we know where we have to find, or rather what intersection we are looking for. So now let's go ahead and make our root locus plot. So before I start making the root locus, just to clarify a little bit as to what transfer function we are looking at when we are making the root locus. So in your lecture notes, a couple of times, if you look at the function, transfer function g, sometimes the gain k has been separated out in the notes, sometimes it has not. But for the root locus formulas or the comments and the rules that we have, what you want to look at is, in this particular case, you want to look at the transfer function that has separated out from the k. So if you were writing GS for this problem, I want to rewrite it as k times another transfer function called ls, and this ls transfer function is what we are is the function for which we are looking at the zeros and the poles. So just to make that clear, so that would be nothing but 1 times all these factors in the denominator. So since all of these factors have been like separated out very nicely for us, we can go ahead and make, or rather plot our poles. So let's start off with that. So we have a -2, and then we have a -3, and then we also have a -7. And if you were to join the real axis segments, again following our rules, that would be one segment, and then that would be another segment which is going to -infinity. So as you can see, again, there are no zeros here, so we will need a breakout point. One of them is already going to -infinity, so this one is fine. But for the other two, we will need a breakout point somewhere in the middle. So let's go ahead and calculate that point. So breakpoint, and I'm using method 1 out of the 3 methods that I had listed last week. So that basically said that we need to come up with an expression for our k as a function of s, right? So since I wrote it in this new form, I can separate out the gain, and that's what I'm using. That's why I've written down ls over there. So k is now nothing but negative of s plus 2, s plus 3, s plus 7. This is nothing but negative, and then we have a cubic expression. And the constraint that we need to set to find out where our breakpoint is that the derivative of this expression with respect to s has to be set to 0. And if you were to differentiate the above cubic expression, we end up with a quadratic expression that looks something like this. And if you were to solve for this quadratic formula, we have s turning out to be either negative minus 5.52 or minus 2.47. So again, you can see that only one of the solutions lies in our appropriate range. So we can cancel out the negative 5.52, and we now know our breakpoint. All right, so again, now since these will be going to infinity, asymptotes are involved, but just because I don't have a lot of time today, what I'm going to do is I'm just going to make a rough kind of guess as to how it goes away to infinity. And we'll use the MATLAB plot as well just to confirm that this is what it kind of looks like. But if you did have to calculate it, you have those straightforward formulas where you subtract the number of poles and zeros and use the angle theta by odd multiples of 180. And for the center point of the asymptotes, you just take the center of these poles essentially. If you have questions about that, you can talk to me in office hours and I can explain that again. But so that's what our root locus would kind of look like, right? And so now we finally have reached the point what we were seeking. We are we essentially want to find the gain at this intersection point where our root locus and our constant damping ratio line meet. So how do we do that? So this is a little tricky. We can't do this by hand quite straightforwardly. Like there is no one formula to just plug in the value and it will give you the final answer. It requires a little bit of a trial and error if you're doing it by hand too. So here we can use MATLAB to help us a little bit. So I've already written down some code from before. I ran it in the first session and it asks me to connect every time. All right. Is it not working? Okay, I think I need to run it again. All right. So this first plot here, so this is what the root locus looks like. So it's very similar to the kind of assumption we had made, or idea that we had of the root locus going to its asymptotes. And you can also see that I have this constant line representing the damping ratio. And you can actually plot that line by using the S-grid function in MATLAB. So you can see I have S-grid in brackets zeta comma 0. Zeta is nothing but my damping ratio, and that has been defined a little earlier on top of the code using the same expression that we just used right now. So the initial input is just the overshoot, right? And so if you're looking at this plot, once again, what you can do is you can use your cursor. So you can use your cursor and bring it to a point of intersection over there. Again, since I'm using this on my iPad, it might be a little wonky, but if you're doing it with your trackpad, it can be a little more precise. So if you bring it up to a certain point and you leave it there or you click on that, the MATLAB will give you all the system properties at that specified point. So you can see that it gives you the overshoot value. Right now it's a little more than what we are looking at, so it's 10.6 and it's 42.6 for that. If I kind of try to target it a little better, maybe I can get a slightly better value. So yeah, it's 40.2 if it's 9.72. So essentially what I'm looking for is that around 41 is what I found out to be where the overshoot value stays at 10%. So from this kind of graphical analysis, we can say that this the gain at this point here is 41. And this is coming from MATLAB. And the point of just making the root locus by hand is also because that's something that they asked you to do. If that was not asked, then you could have just used MATLAB for the entire problem. And now the final part that they're asking us here is that what is the appropriate static error constant. So this is nothing but your static position error constant. I think this was covered a couple of lectures ago. I'm not exactly sure what the lecture number was, so if you want to ask that, again, you can let me know during office hours. But essentially, there are three types of error constants that have been defined in the lecture notes: position, velocity, and acceleration. So if you're looking at a specific variable and the rate of change of the variable, you look at the velocity error constant. If you're looking at the rate of change of the rate of change, then you're looking at the acceleration constant. Here nothing has been specified, so we are thinking that we are looking at the variable itself. So we are looking at the position error constant, and that is nothing but kg, and that is defined by limit of s going to 0 for our transfer function gs. And so if you're looking at this particular point here where the gain is 41, our error constant would be 41 divided by that, and S is tending to 0. So this is nothing but just 41 by 42, approximately 0.97, something like that. But something to keep in mind here again is that this is not the steady state error, this is an error constant. The steady state error, this that I'm defining by E infinity, would be given by 1 divided by 1 plus kg. And so for the current case, we have something like that, and this is approximately around to 0.5. So as you can see, the steady state error is a little different compared to your error constant. And again, you want to be careful that which formulas you're using for the error constants. Like I mentioned, there are 3 types: position, velocity, and acceleration. So if the question does specify which error constant they are asking for, the formulas change a little bit, and the formula for the steady state error also changes a little bit. So you want to make sure that you're using the right formula. Any questions? All right. So looking at part B is nothing but doing this in MATLAB. So you can just plot the step response, and I think the code that I wrote right now is perhaps not working properly, or I need to check it once again. But the plot that you should get is something like that, like you will have some overshoot and then it goes to a steady state value. I think my code right now is giving me a result something like this, so I think I might have messed up something. So I need to check that once again. But if your plot looks something like that, that should be good. Yeah.
When you do that, do you use the function that's given, or do you find the...
So we use the close, so basically the code is, if I just bring up my code, yeah, so I have this, I'm defining my feedback system, which is feedback system transfer function, comma 1, that's the unit feedback, and then I'm plotting the step response for that.
Okay.
Yeah. All right. Any questions? So again, I'll make the right plot for this and